In statistical inference, we're interested in determining the plausibility of different values of an unknown parameter. For example, we may want to determine the proportion of the population that has diabetes. It would be impractical, if not impossible, to ask every single person whether they have diabetes. Instead, we want to estimate the diabetes rate based on just a few individuals. Before we collect any information about diabetes, we may not really have much of an idea of how many people in the population have diabetes. It could be very close to 0 or very close to 100%. We don't really know. The diabetes rate could be any of these values. Without any background knowledge, they're all equally plausible. To get some kind of idea of the diabetes rate, suppose that we ask 20 people whether they have diabetes, and we find out that 3 of them do in fact have diabetes. Based on this new information, what's the most plausible value for the diabetes rate? The posterior distribution tells us how plausible each possible diabetes rate is, given the data that we've collected. Here's the posterior distribution given that 3 people out of our sample of 20 had diabetes. What's the most plausible value? The mode of this distribution is 15%. Based on our sample, the most plausible diabetes rate is 15%. This is called a point estimate. A point estimate is a single number that is a best guess for the parameter. It's a measure of central tendency of the posterior distribution. That means it could be the mean, the median, or the mode. In our diabetes example, we use the posterior mode of 15% as our point estimate, or best guess for the proportion of people in the population who have diabetes. A point estimate tells us our best guess, but it doesn't communicate how confident we are in this guess. Is it a really good estimate or just kind of a vague idea? After all, even though the most plausible diabetes rate is 15%, there are other proportions that are fairly plausible as well. The diabetes rate could be 10% or 20%, for example. In fact, there's a range of plausible values that would each be a reasonable estimate for the diabetes rate. Instead of stating a point estimate, our single best guess, we could use a credible interval. A credible interval is a range of values that represent a given level of plausibility. It's based on the posterior distribution. If we add up the plausibility of all the values between 5% and 31% based on the posterior distribution, we'd arrive at 90% plausibility. In other words, given that 3 out of our 20 people had diabetes, we believe there's a 90% chance that the population diabetes rate is between 5% and 31%. The range 5 to 31% is a 90% credible interval estimate for the diabetes rate. The width of a credible interval gives an indication of how confident we are in our point estimate. If the credible interval is narrow, then we're rather confident that the diabetes rate is very close to the point estimate. However, if the credible interval is wide, then there's a fairly large range of plausible values for the diabetes rate, and the point estimate, despite being our best guess, is more of a general idea than a precise estimate. Any range can serve as a credible interval insofar as we can compute the plausibility of values in any range. For example, instead of looking at the range from 5 to 31%, we could find how plausible it would be for the diabetes rate to be between 50 and 100%. Not very likely, in fact. According to the posterior distribution, we believe that there's less than 1 in 1,000 chance that the diabetes rate is over 50%. But what about another range, like the range from 0 to 29%? Based on the posterior distribution, we believe that there's a 90% chance that the diabetes rate is between 0 and 29%. The range from 0 to 29% is also a 90% credible interval for the diabetes rate. Or we could look at the range from 9% to 100%. Based on the posterior distribution, we believe that there's a 90% chance that the diabetes rate falls between 9 and 100%. All 3 of these intervals, from 0 to 29%, from 5 to 31%, and from 9 to 100%, are 90% credible intervals. Each of these intervals is a range of plausible values that represents 90% plausibility. Given that all of them represent 90% plausibility, which interval should we choose to communicate our beliefs about the diabetes rate? The range from 9 to 100% doesn't seem to be terribly useful. It's so incredibly wide that if we say the diabetes rate is somewhere between 9 and 100%, we haven't really said much that's useful. It's not all that different from saying the diabetes rate is somewhere between 0 and 100. The range from 0 to 29% is more useful in this regard because we've limited the plausible values to a narrower range. But along those lines of thinking, the range from 5 to 31% is even better, because it's only 26 percentage points wide instead of 29 percentage points wide or 91 percentage points wide. Even though each of these ranges covers 90% of the posterior plausibility, the 5 to 31% range is the narrowest, so it homes in most tightly on the most plausible value. Notice that the 5 to 31% range also includes the part of the posterior with the most plausible values in it. This range from 5 to 31% is an example of a highest density interval. A highest density interval is the narrowest credible interval for a given level of plausibility. It's also the credible interval that includes the values that are the most plausible. The highest density interval, or HDI for short, gives us a range of the most plausible values for the diabetes rate, and thus acknowledges that our knowledge of the diabetes rate is not perfect. Based on our sample of 20 people, we've narrowed the range of possible diabetes rates from 0 to 100% down to the most plausible values between 5 and 31%. Based on the information we have so far, we're fairly confident that the diabetes rate is somewhere in this range, but it isn't absolutely certain. There's still a 10% chance that the diabetes rate could be outside of this range. If you've taken a statistics course before, you may have heard of confidence intervals. Confidence intervals and credible intervals are similar. In fact, some confidence intervals are also credible intervals, but there are important differences. Using a confidence interval is like tossing a ring around a post. If I give you a ring of a certain size, you could toss the ring toward the post a bunch of times to figure out how often you could get the ring around the post. If I gave you a larger ring, it would be easier to ring the post, and your proportion of successes would go up. If I gave you a smaller ring, it would be harder to ring the post, and your proportion of successes would go down. If we had a lot of time and patience, we could keep trying different ring sizes until we found the size of the ring that you would need in order to be able to ring the post 95% of the time, given your particular level of skill. In this analogy, the post is like the population parameter, and where your ring lands is like the sample statistic from one study. The ring is like the confidence interval. Each time you conduct a study, that is, each time you toss the ring, you calculate a confidence interval. Sometimes the interval will include the population parameter, that's when you ring the post, and sometimes it won't. The size of the confidence interval, that is the size of the ring, determines how often that type of confidence interval will include the parameter, if you conduct many different studies. You can choose the size of the ring strategically so that before you toss the ring, you have a 95% chance of getting it around the post. However, once you've tossed the ring, there's no longer a 95% chance that the ring is around the post. It either is around the post or it isn't. Similarly, confidence intervals are based on a logic of repeated sampling. You choose the size of your confidence interval, your ring, so that out of many different tries, your confidence interval will include the population parameter about 95% of the time. But once you've conducted your study and found your specific confidence interval for this particular estimate, there is not a 95% chance that the population parameter is in the confidence interval. It either is or it isn't. This is a common misconception about confidence intervals. Even though the confidence level of 95% is based on the idea of repeated sampling, out of many tries you get 95% of them right, people treat them as if they were probability statements about the plausibility of a parameter in a given range. In other words, people often treat confidence intervals as if they were credible intervals. A credible interval, on the other hand, is actually the statement that people want to make about the strength of our beliefs of the plausibility that the parameter falls within the given range based on the posterior distribution.